Okay, session is being recorded, and I'll start this, and then I'll start this. Okay. Okay. So, so the other webcam arrived. Woo! Not in time to be useful, but better late than never. It's 11:35. It's 11:35. So the longest increasing subsequence problem is fairly simple to state. So you have a sequence of numbers like 2, 7, 5, 1, 6, 4, 9, 8, 3, 2, 10, I don't know, 9 again, 12 or something. Okay. Yeah. Yeah, okay. No, let's make it 12. Just to make it. Okay. So you want to find an increasing subsequence. An increasing subsequence is, can everybody hear me? Yes, I think I'm recording, yes, I'm recording both things. Okay, so for example, 1, 4, 8, 10, 12 is an increasing subsequence. Okay? So a sequence doesn't have to be, the elements of a subsequence don't have to be consecutive, but otherwise it would be a substring. So a substring is a subsequence, not all subsequences are substrings. And we're going to want them to be, sometimes people mean, when they say increasing, they actually mean non-decreasing, which means that you can have doubles. But just to keep things simple, we're going to mean strictly increasing. So you want 1, 4 is larger, 8 is larger, 10 is larger, 12 is larger. Okay, but we want to find the longest increasing subsequence. So this is going to, and we're going to do this with dynamic programming. So it's not that bad. If you think about it from, remember I was saying that, imagine that you have this friendly, weak-willed professor who will tell you solutions to subproblems which are smaller. Okay? So how would you do this if you could ask somebody, your professor, and you could say, well, Prof, what's the length of the longest increasing subsequence that ends within, we have to be a bit careful. Instead of just saying the end that is within this prefix, we're going to say that ends here, that ends with this element. Because, because that works. So, for example, suppose that you could ask, suppose you wanted to find out what's the longest subsequence that ends. So once you know the longest subsequence that ends at each element, you can just, you can do one scan and find the longest subsequence. So suppose you want to know the longest subsequence that ends at 9. So what questions would you ask your professor? Well, you wouldn't ask what's the longest subsequence that ends at 10, because that's no help for you to figure out what's the longest subsequence that ends at 9, because 10 is bigger than 9. So you can't take a subsequence that ends at 10 and make it end at 9. But you could ask, okay, what's the longest subsequence that ends here? What's the longest subsequence that ends here? What's the longest subsequence that ends here? Here it's no use because this is smaller. So here, 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 and so on, going backwards. So we're going to take that idea that you can ask for each number. You would go back and you would ask for all of the previous numbers which are smaller. So you ask what is the length of the longest subsequence that ends at each of the previous numbers which is smaller, and then you take the largest length, and then you say, okay, well, for example, suppose the largest length is this one, and the length is 4. I haven't worked it out. Maybe it is. Maybe it isn't. But then, if the longest subsequence that ends at any of these numbers which is less than 9 is here and it's length 4, then here you could say, oh well, in that case it's going to be length 5 because I would take the subsequence ending here, and I would add a 9. Yes. So, and then we're going to do that for 12, and then we're going to do that for 11, and then we're going to do that for 12. Okay, so why does the value matter? The list is unordered. Yes, but if, for example, you ask me what's the length of the longest subsequence that ends at 10, and I tell you 6, that doesn't help you compute the length of the longest subsequence that ends with this 9. Because you can't put the 9 if you said 1, 4, 8. Okay, so it's not going to be 5. It's going to be 4 here, and then you said 10. Well, you can't append the 9 to this because the 10 is too big. And you're not actually, without looking at these numbers, you're not even sure that you can replace the 10 with 9 because maybe this has a 9 in it. And then you can't include that 9. Okay? So the subsequence is ordered. Yes, the whole list is not ordered, but the subsequence is increasing. So now we turn that idea around, and instead of you asking about things at the end, you're going to not use your helpful, friendly, spineless professor. You're going to sort of do this for yourself, and starting at the beginning. So that way, you will always know, when you get to this 9, you will have worked out all of the lengths of the longest increasing subsequences that ended all of these elements. So let's start with that. The longest increasing subsequence that ends at 2 has length 1, and it is just that 2, right? That's easy. Okay, so 7, we look back through all the numbers before 7 that are less than 7, and we find the largest length, which is 1, and we add 1. So this is 2. Okay, can you read this? Okay, good. Oh, this webcam is so cool. So we do the same thing with 5. We look back, we ignore 7 because it's bigger than 5, greater than or equal to 5. And so the only thing we can add to is this list of length 1 that ends at 2. So this is a 2. 1, we look back through all the numbers which are less than 1, which is nothing. And then we say, okay, so the longest list is like 0. So we add 1, so this is a 1. Here, we look back through everything that's less than 6, which is everything except the 7. And we say, okay, so what's the longest length? It's this 5. It's the list that ends increasing subsequence that ends at this 5, which has length 2. So this has length 3. For 4, we look back, we ignore the 6. The 1, so the 1 would give us a 2, the 5 we ignore, the 7 we ignore, and the 2 would give us a 2. So we have a 2. Now we look back, the 9, everything is less than 9, so we take the biggest number, which is the 3, and we add a 1, and we get 4. So before we go any further, somebody asked and said it really changes the algorithm. Where's my blue pen? Okay, so it really changes the algorithm if we're just returning the length or we're returning the whole list. But it doesn't, because if we wanted to return the whole list, now what we could do, 2 is just that. 7, we just store a pointer to the number where we found to the largest, so the number less than 7 that had the largest length. That 9 looks like a 5. Which 9? This 9. Okay. Okay, yeah, okay, sorry. Will do. So 5 also goes here. We store a pointer to this. 1, we don't store a pointer. 6 points to 5. 4 points to either 1 or 2. 9 points to 6. Okay, so 8, what do we do? Okay, so 8, we go back through here, we ignore the 9 because it's bigger than 8. So we look at the 4, this would give us a 3, this gives us a 4, this gives us a 2, a 3, a 3, a 3. So we say, okay, the best we can do is a 4. Writing a bit bigger. Writing a bit bigger and very messy. And it also points back to the 6. Okay? So 3, we ignore the 8, we ignore the 9, we ignore the 4, we ignore the 6. We look at the 1. The 1 would give us a 2. We ignore the 5, we ignore the 7. And the 2 would give us a 2. So we get, okay, I'm mixing up the counts. We get a 2. And it can point to the 1. Okay. 2, we go back. The only thing that can actually that's smaller than 2 is a 1, so we get a 2. And it also points at the 1. 10, everything. So we go back, and the biggest number we find is a 4, which is either at the 9 or at the 8, so maybe we take the 8. So that's going to give us a 5 here. Remembering to write bigger. It's going to point at the 8. The 9, we ignore the 10. This would give us a 3. This would give us a 3. This would give us a 5. This would give us, we can't take this, we ignore it because we want something strictly increasing. This would give us a 3, a 4, a 2, a 3, a 3, a 2. So we take this, the 4, this gives us a 5. We store a pointer. 12. Best we can do, we go back and look at everything. The best we can do is a 6, which is like this. 11, we go back, the best we're going to do is a 5. So that's going to give us 6. And then at the 12, this will give us a 7. We ignore this because the 12 is equal. This will give us a 6, a 6, a 3, a 3, blah, blah, blah. We go back through all the stuff. So the best we're going to get is a 7. And it points here. Now, in this case, okay, just to make this a nicer example, I'm going to add another number. I'm going to add a 5. Because that, for the 5, we look back, these, so this is actually roughly, okay, the 5, this would give us a 3, ignore this, this would give us a 3, we ignore this would give us a 2, this would give us a 2, so the best we can do is a 3. No, red. The black marker is running out of ink, so I'm kind of trying to, okay, so a 3. This is just to highlight the fact that the biggest length, wait, what was 4? Where? 4? What is 4? What's supposed to be 4? Back at 8. This is a 4. It is a 4. Okay. Sorry. So, mixing up pen caps. So, then we scan and we say, okay, the biggest length is 7, and if we actually want the sequence, then we have it because each thing stores a pointer to the previous number. So we say, okay, 7 goes. So the biggest number, the biggest length is 7, which is the 12. It points to the 11. The 11 points to the 9. The 9 points to the 8. The 8 points to the 6. The 6 points to the 5. And the 5 points to the 2. 1, 2, 3, 4, 5, 6, 7. Ooh, magic. So we're all happy, except we're not super happy because this is kind of slow. But let's think about, well, first of all, let's write the recurrence. So let's call this red array A. So let's call the blue array, what are we going to call the blue array? B, yeah, B. For blue, and the red array is going to be R. What a mess. Okay, B and R. So what are we going to say? We're given B as an input. Yeah, B is a good name for a blue array. So we're going to say that AI is the length of the longest increasing subsequence that ends at BI. Okay, so that's what we want, because that way, obviously, when we're finished, we just scan A, and not A, R. Ri is the length of long increasing subsequence that ends at BI. So that way, if we manage to compute R, we just scan it, and if we're just returning the length, then we return the largest number in R. And if we want to return the actual sequence, then we need this array of pointers, which we will call G, and then we find the biggest number in R, and then we walk backwards following the pointers in G and return this. Yes, A should be R, sorry. So how are we going to do that? Well, we said that Ri is max over J, where J is, are we counting from 0 or counting from 1? Let's count from 0 so that this is actually going to be easier to write in C later if we want to. So J is greater than or equal to 0 and less than I. And it's going to be Rj such that Bj less than, wait, no, yes, less than Bi. So we're saying we're looking for the largest length that ends at something that is less than Bi. So we find this largest length and then we add 1 because we can add Ri. And then we have to, we have to define this so that if this is empty, then this is 0, and then we add 1. But like that's just, you handle that case. So this is recurrence. So how do we do this? Well, we just say for I equals 0 to n minus 1. For j equals 0 to I minus 1. And then I realized, oops, I should have stuck a max in there. So max equals 0 for j equals 0 to I minus 1. If bj less than bi and rj greater than max, max equals rj. Is this right? And if and for and for, so whoop, whoop, whoop. And then you write something else which scans R and returns the biggest number. Okay, everybody can do this. All of my whole 19 students. What does the if statement say? If bj is less than bj, sorry, bi, and rj is greater than max. So you're checking and you're saying, if I want to find the maximum value between R between R0 and Ri minus 1, but subject to the condition that, so I'm looking for the biggest Rj, but subject to the condition that Bj is less than Bi. So yes, this should be an I. Sorry about that. Oh wait, okay, then what I should do is I run through here, and in this place, I should say, before this N4, I should say, oh, actually, I don't even have to have the max. What I can do, okay, so it's time to do this, start this camera again. Okay. I don't have to say max, I can say RI. And then I don't have to. Okay. So, and this should be RI. So without testing it, I think it works, probably more or less. And otherwise, I mean, it could be patched and it could be made to work pretty easily. But what's the problem? So how long does this take? Do we still need to add RI equals max after the inner loop? No, not if I do this, I think. So I'm getting rid of one variable. And yeah, okay, I'm not sure. Okay, sorry, yes. How fast, how much time does this take? B is the input. We are given B. B drops from the sky. So some user gives us some sequence of numbers, and we are asked to find the longest increasing subsequence. Why? Who knows? Because they will pay us to do this. Or maybe there is a reason. But the reason doesn't actually affect how you implement this. R, yes, R, we define R so that Ri is the length of the longest subsequence ending at Bi. Okay, good. So we have n to the n. Not quite that bad. Not that it's not great, but it's not bad. This is an assignment. It's constant time. This is an if statement. This is constant time. This is a for loop. So it's going to take like time I. This is an assignment. It's constant time, and this is another for loop. So we have two nested for loops. So for I from 1 to 0 to n minus 1, and for j from 0 to I minus 1. So it's going to take quadratic time. So this is going to be O n squared. So that's not bad. How much space will it take? It will take like O of n, because apart from B, the only stuff we're using is R, and maybe this other green array G of pointers if we want to actually return the sequence. So O(n) time, O(n) squared time, O(n) space. So, not terrible, but I mean not terrible if n is like 1,000, then it's okay. But if n is like 1,000,000, then it's not so good. So we're going to speed it up. And did that only take? That only took like 30 minutes. Oh, okay, this is going to be a fast lecture, maybe. Well, what I can do, yeah, okay. No, it doesn't have to be that fast. So, we can think of this almost like a geometry problem. Okay, so let's get rid of this. So if you can hear that rattling, that's just my fridge. So imagine that we have actually no, this line doesn't exist. Imagine that we sort of have a grid. We have the plane, and this is 0. What's the biggest number I've got? Well, that doesn't actually matter. The biggest number I've got is a 12. Okay. Sorry, these, I know these are kind of small, but these are just numbers from 0 to 12. These numbers will be bigger. I can even make those numbers bigger. Let's make those numbers a bit bigger. I can make them a lot bigger, but a bit bigger. Okay. So what I'm going to do is 2. So when I start out, I say 2. Okay, I want numbers smaller than 2, and I want the biggest. So there's nothing, so I'm going to put a dot here. Okay, which means this is, it has, the key is sort of 2, and it has some associated, it has length 1. Clear? Okay, then I have 7, and I say, okay, 7, I want sort of the biggest number, the biggest length of a number less than 7. So I'm asking for the highest point to the left of 7, which is 2, which is this 2, 1. Okay? So I say, okay, I take this 2, 1, and then I'm going to put a dot here. So this is, and this is 7, 2. Now, I take 5 and I say, what's the highest point left of 5? Well, this is 2 as well. So it's going, I'm going to take that. Okay. So 1, there's nothing left of 1, so this is a 1. Uh, 6, so what's the highest thing left of 6? What's the highest thing left of 6? Is this 5. Woohoo. So this is going to be, this is going to give me a 0.63. Okay? So you can view this as a query on a grid, right? Where I'm asking at each point I'm saying what is the highest point to the left of my new value, and then I take it and I add a new point. So 6, 3, and then 4. What is the highest point left of 4? It's either of these. So I get 4, 4, 2, 9. What is the highest thing to the left of 9? It's this one. So I get 9, 4. Okay. So people can see that if I had, for example, a magic data structure that would let me do this, that would represent this grid, and I didn't restart that timer. Oops. So this should be 15 minutes now. I don't know. I mean, maybe the Collaborate Ultra. Oh, good. The Collaborate Ultra is recording. Good. Maybe the Collaborate Ultra is sufficiently high resolution that I don't even need my other little camera here. But, okay. So do people see what I'm doing? And how, if I had a magic box that represented this grid and let me query what is the highest point to the left of such and such, what does the x represent and the y represent? The x is the b value, and the y is the r value. So I'll just put this is sort of the d, and this is the r. So, okay, let's do the next point after the 9. So the next thing after the 9 is an 8. What is the highest point to the left of 8? Well, it's this 6, 3. And so we take the 6, 3, and we can build on it, and we get something that's one more, and so we get 8, 4. And then the 3 was the highest thing to the left of the 3. It's either of these 2 points, so we get a 3, 2. So if you had this magic box that would let you do this, where you would say, what's the height of the highest point to the left of x? And it would come back and say y. And then you can say, okay, in that case, insert point x, y plus 1. Right? So you want, what are the operations if you have a data structure that does this? You want to query what is the height of the highest point left of, and you want to say bi. So this is your x. And then you say insert, well, okay, let's just make this a general x. Insert point x, y. So this is your query, and this is your update operation. Okay, so if you had this, you could implement this algorithm. Say that you have this algorithm, this data structure that does these two things in time f of n, where n is the current number of points that it's storing. Then you could do this in time O of n f of n, right? because for each of these points, instead of doing this whole loop through J finding the max, you would just ask the data structure. What's the highest point left of this? And what's the height of the highest point left of this? And give it that, and you would just take that and add 1. And then if you wanted to store these pointers, you would actually ask, what is the point? What is the highest point? And then you would store a satellite data, a pointer from your new point to the previous point. Okay? So, how are we going to do this? So there is on LeetCode a very sneaky way of doing this. That's just using an array. But as I said, the explanation is horrible. It's correct, but the code is correct, but the explanation actually isn't correct. Or at least it doesn't explain why it does what it does. It doesn't explain why it's working. So I'm going to teach you a more general technique, which also results in an n log n time. The solution on LeetCode is very brittle. It needs the problem to be exactly like that. I'm going to teach you a technique which is more general and more powerful. And so LeetCode, the solution on LeetCode can it can basically more or less only do this, but the solution I'm going to teach you, the data structure I'm going to teach you, which is sort of, I think, the nicer way of doing it, is you can actually say, what is the highest point in a certain range? Where you can say, okay, to the left of 8 and to the right of 3. And then, so it can support a more general kind of query. So obviously, if it can support that query, it can also support the query, okay, what is the highest point to the left of 8? Because then you just say, okay, well, in that case, it's to the left of 8 and to the right of minus infinity, or to 0 in this case, if you're only allowing non-negative keys. So I'm going to teach you how to do how to implement a data structure that does that. Okay? So, but this requires me to ask you some stuff. I know in the fall semester, a bunch of people told me that they didn't know AVL trees. I don't actually care if you know AVL trees in particular, but do you know AVL trees, or red-black trees, or 2-3 trees, or like any of these other self-balancing binary search trees, splay trees? No. AVL trees, yes. Okay, so yeah, this is, apparently there is a difference between the sections of 2110. So I do not have time to teach. Okay, so I'm going to do with AVL trees. Okay, so it doesn't actually require, maybe I have to modify the midterm a bit then. Maybe. So the thing is, it doesn't. So I mean, we can. I hope you all know binary search trees. Forgetting about the self-balancing thing. So I can do this explanation in terms of. First, I'm going to do the explanation in terms of just trees, just binary search trees. And then we're going to sort of add the self-balancing bit on top. And the only problem is to show you really how it works. I sort of have to crack the things open, and we have to get inside and look at how you actually modify the AVL rotations. But you don't really have to worry about that, because like nobody, I have to look up rotations every year when I teach it. So we still want to do RI, but we can remember what this means. This is the definition, and this is the slow way that we this is the slow way that we implemented it. But now we're going to forget about this, and we're going to think about, actually, yeah, let's forget. Oh, drat, I shouldn't have done that. Let's suppose that now we're going to say for I equals 0 to n minus 1. And now we're going to say Ri equals 1 plus height of highest point left of BI. And then we say insert the point BI RI. And 4. So it got much shorter. And if we can get these two operations on this data structure, so I should have actually written this in as a data structure query, but this is pseudocode. So if we can say how to implement this data structure, then this is going to take n time times the time for this query and the time for this update. Okay? Good. So the first idea is we're going to insert things into could we do it in a tutorial? Maybe. But the tutorial this week is going to be a help session for the assignment 3. Maybe. I will think. I'll think about this. Okay, and I just have to check and see. I just have to see how much time we have on the clock before I have to restart this thingy. We have 2 minutes and 40 seconds before I restart this camera. Okay, so what we're going to do, suppose that we're just going to insert for the moment, we're just going to insert the BIs. Okay? So, yeah, so we remember this. So I can get more board space so that I can write nice and big. So we remember how to insert into a normal binary search tree. So we just insert 2. Okay. And then we insert 7. And then we insert 5. And then we insert 1. And then we insert 6. And we insert 4. and insert 9, and 8, and 3, and 2. Is this going to be less than or equal? Yeah, less than or equal, say. So this is going to be 2, 10, 9, 12, 11, 12, 5. Okay, so it is not balanced, right? No, nowhere near balanced, actually. But everybody remembers how to insert into a binary search tree. Okay, so the cool thing about a binary search tree is, suppose this has height h. So I can actually, if I give you pick a number like, okay. Yeah, so hope it's focused. And we restart. So I have, no, okay, but now we reset. Now we turn it on to 25 minutes. Maybe this isn't going to be a short lecture after all. If you choose, pick a number, say 5, it's possible to sort of cut this tree into stuff less than or equal to 5 and stuff bigger than 5, right? Because, and it's one line that goes down here. So you can, if you walk down from the root, okay, how do you find this line? How do you find this line? Well, 2 is smaller than 5. So everything over here is smaller than 5. 2 and everything to the left of 2 is smaller than 5. 7 is bigger than 5. So everything, this 7 and everything in this right subtree are bigger than 5. So we don't want any of this. So we don't want any of this, we don't want any of this. Now, but we don't know about this. So we look, 5 is equal to 5. So everything in its left subtree is less than or equal to 5. But the 6 is bigger. So the 6 and anything in its right subtree is going to be bigger than 5. And then maybe 6 might have a left subtree, and then, well, actually, we've already seen the 5, but maybe we're looking for 5.7 or something. So then we're going to keep going down and looking in the left subtree. So as we go down, we can okay, too small, don't care about that and anything in its left subtree. Too big, don't care about that and anything in its right subtree. As we go down, we sort of find this dividing line. How long does it take us to find that dividing line? Well, time h, at most order h. So in fact, the other thing you can do is, the other thing to notice is that if we just want the which are, if we want to sort of split this into trees, subtrees, which contain stuff that's less than or equal to 5, everything in the left child of 2 is less than or equal to 5. Everything in the left child of 5 is less than or equal to 5. And the 2 and the 5. So if we're looking at stuff less than or equal to 5, how much people can, and we can give back a subtree as a pointer to its root or something, then it takes us logarithmic time, sort of order h time, to sort of give back pointers to all the stuff less than or equal to 5, because we get say, okay, this 2, we can't say this whole tree is, but we can say just this one node, and just this one node, and this subtree and this subtree. Right? And I didn't start the timer. God, no, start, not start. How much time do I have? Oh, okay, I have 23 minutes. So this is the main idea for these. Well, this is a main idea. Okay, so we can find the subtrees and these single nodes less than or equal to 5, and we can do it in order h time. So if h were somehow magically logarithmic all the time, then this would take logarithmic time. Okay, to sort of consider all the stuff which is less than 5. So given any key, we can find this, we can enumerate a logarithmic number of subtrees and nodes such that together those are all the stuff that is less than or equal to that key. And in fact, remember I said that on LeetCode there's a solution which is very brittle, but in general we can choose a range. Well, we can also do that if somebody said, okay, I want everything that's less than 5 but bigger than 3. Then you would have these 2 lines, but bigger than 3. Here, you would do this again. You say, that's smaller than or equal to 3. That's bigger than or equal to 3. That's bigger than or equal to 3. So then you get this area of stuff between the red lines. You just do 2 divisions, and you get everything that's, sorry, if it's bigger than or equal to 3, then it includes 3. That's bigger than or equal to 3, but less than or equal to 5. Okay, so you see how if you're given a binary search tree of height h in time O of h, you can find these O of h subtrees which contain keys within a certain range. Maybe? So, nobody's saying anything, so I'm going to assume it's okay. Did I insert everything? Okay. Okay, so now, so far, nothing new. I mean, we had the dynamic programming, that was new. But, and then we have this data structure you want, and that's new. But now we have to augment a binary search tree. And this is one of the learning objectives of this course. So it's important. So now, when we, I'm gonna reinsert this. I'm gonna redo this. Now, I'm going to insert the B's the B's as keys, so I insert 2. But I insert also, I put, this is not the key. This is satellite data. I put the R value. Now I look at 7 and I say, okay, well first, before I insert the 7, I do this thing. Okay, I find everything smaller than 7, and I find the largest red value of everything large. The largest red value in the tree of keys less than 7. So I have 7. And this is going to be a 2. Now I get 5. So again, I look and I'm going to do this split. I'm going to find everything smaller than 5. Now remember, when I do that split, I find everything smaller than 5. It's going to store, it's only going to be a certain number of, logarithm, order H subtrees. So the trick is, actually I'm going to have a 1 in red. But what I'm going to be doing, I'm going to store the individual keys, but then I'm also going to store the largest red value in the subtree. So that I'm going to store as a green value. Green is now not a pointer. Green is a maximum in the subtree. So I'm going to, when I insert 5, I find the part of the tree that contains keys less than 5. That makes it this node, but not this node. And then, but it might also have some subtrees. It might have some complete subtrees. Those complete subtrees, the maximum value in the subtree is stored at the root in green. So I don't have to look at the whole subtree, I just look at the root. So the C5, I see it's this, but it's not the whole subtree because it's not the right child, it's not the 7. So I ignore the green 2, and I just look at this. So I get 5. Too many pens. I get 5. 5. The biggest red value of a key less than 5 is 1. So 5 is going to be 2. And the largest green value is in its subtree is 2. This doesn't change, okay? Because it's already 2. This was already 2 because of this 2. So when I started, this would be 2, 1, 1. Then I inserted the 7 and became 7, 2, 2, and this became a 2. This is 5, 2, 2. Okay, 1, 1 goes here. There's nothing to the left of it, so this is a 1. This is a 1, and so this doesn't change because this is still bigger than this. Am I losing anybody? Oh, I lost one person who left the session, but okay, 1, 6. Okay, now we're gonna first thing, remember that query. What is the what part of the tree has keys less than 6? So it's this, but not this whole subtree, because not this. So it's just this. Which numbers do we look at? We look at this one. This is the whole subtree, which happens to be just one node at the moment. But so take the maximum, which is 1. So we take the max of 2 and 1, and then this, it's the whole subtree, which happens to be just one node, which is 2. So it's the max of 2, 1, and 2. And we ignore this line now. The max of 2, 1, and 2 is 2. So we take 2 add a 1, and we get 3. So we get 6, 3. The max in this subtree is 3. And that means that now we have to walk up the path of the root. And this is now a 3. And this is now a 3. And this is now a 3. Am I losing anybody? I've lost one person. But it's not the end of the... No, I have 15 minutes. Okay. So now 4. 4, what is the part of the tree that is less than 4? Well, it's this. So we don't look at the green 3 because the green 3 is the max in the whole tree, and this part of the tree has stuff bigger than 4. So we look at the green 3 and the the red 1. We ignore the green 3. We look at the red 1 and we look at the green 1 because this whole subtree is less than 4. So that is going to give us a 2 because the red 1 and the max of the red 1 and the green 1 is 1 plus 1 is 2. So this becomes 4, 2, 2. And we don't have to change anything because these are 3's. Okay, then we get 9. 9 is going to be, so we take everything smaller than 9, which is actually the whole tree in this case. And so if we take everything smaller than 9, we just look, then all we have to look at is this green 3, because the whole subtree is smaller than 9. So this green 3 is the maximum of all the red values in the whole tree. So we put 9 in, and it's going to get 3 plus 1 is 4. And the maximum in its subtree is 4. And then we have to walk up to the root. And this is a 4, and this is a 4. Sometimes you only have to walk up a little bit of way, because if this had been like a 3, and then this had been a 5, we would just change this one. Okay, so 9 is a 4, then 8. Normally, I would be making people do this. I'm like, what's this? Where do I put this key? What is the red value? What is the blue? But this is not going to work. I'm also running out of time. So we're going to put in, first we're going to say, next thing is an 8. What part of the tree contains keys less than 8? Well, it's this whole subtree and this whole subtree plus this node and this node. Okay, so we're going to take the max of, because it's just this node, we don't take the max of this. We just take the red 1, because this is just this node value. But then we take the green 1, because this is the max of this whole subtree. We don't take the green 4, because that would include the 9. So we take the 2, and we take 3, because this 3 is the max in this whole subtree. So the max of 1 and 1 and 2 and 3 is 3. So we're going to put 8 in with a 4. 3 plus 1. So 8 goes in. I really hope this stuff is not toxic. I must have absorbed so much of it through my fingers in the past couple of decades. Okay. So 8 is 4. 8 is 4, and the max in its subtree is 4, and the max, these don't change. 3, what's less than 3 is like this stuff, so it's subtree and this node. So it's maximum of 1 and 1, so it's 2. 3 and 2 and 2, and nothing changes. And then 2 is the only thing smaller is this one, so it goes in with 2 and 2 and 2. And then we get to the, like, an interesting bit, and then I'm going to stop after this 10, because the 10 goes in, and you say, the 10's not so interesting. Everything's smaller. So we take this 4, we add the 1, we get 10, the max 5, and this is a 5. And then we have to erase these and make this a 5, and make this a 5, and make this a 5. Okay, so I hope, so people can see that in general, the time to find the maximum is going to be, remember, when we do this cut into stuff smaller, then that we get back, if the tree has height h, we get back h single nodes and subtrees. And we just have to look at the root of the subtrees. So in total, this query takes order h time. And then to do the insertion takes order h time, because it's a binary search tree. And then to update the maxima stored at the ancestors takes order h time. So this whole thing is going to take order h, so it's going to take, as we're inserting, it's going to take order h time. So if you insert keys in a random order in a binary search tree, it tends to have, it usually has height about log n, but that's not guaranteed, because the blue sequence can be chosen adversarially. So what you have to do to guarantee you've got running time n log n is to use a balanced binary search tree. That gets a little bit tricky. Like, normally you just be like, yeah, I use a balanced binary search tree, and the height is always logarithmic. So automatically, I'm going to get height, I'm going to get running time and log n, because my query has remember our query of what's the max, what's the maximum red value associated with a key that's less than such and such, or you can also do less than, more than, in this range, more than such and such, but less than such and such. That's going to take time log n, and then to do the insertion and the updates is also going to take time log n. The only tricky part, which I am not probably going to be able to do in 7 minutes, is the fact that when say in an AVL tree, you have to do a rotation. I can maybe do it in 7 minutes. You have to do a rotation. When you do a rotation, normally in an AVL tree, you just have your keys. But now you have your keys, the red values are associated to those particular keys. So the red values, when you do a rotation and you rotate the blue keys, the red keys go with them. But now you have these green values, which are the maxima in the subtrees. So now when you do a rotation, you have to be careful not to mess up your maximum. So let's look at one. Let's try to do this properly. So for the people who haven't seen AVL trees, they're not hard. They're not in the book because the book teaches red-black trees. But basically, what you've got, the rule for an AVL tree is that it's just a tree, right? But at each node, the subtrees are sort of balanced in that their heights differ by at most 1. Okay, so you store this extra little piece of balance information in each node, which says, is my left subtree deeper than my right subtree, or is my right subtree deeper than my left subtree, or are they equal? Because my left subtree is deeper than my right subtree, it's deeper by at most 1. Well, if it's deeper by exactly 1. And if they're equal, then the balance is 0, and if the right, so it's usually expressed as -1 means the left is deeper, 0 means they're equal height, and 1 means the right is deeper. So when you insert something, it's possible, or delete something, it's possible that one of the subtrees breaks this balance condition, and then you have to do something called rotation, which is just like you like juggle the stuff around until the balance condition is restored. And there's a particular way to juggle the stuff around, this rotation. So, let me see if I can remember how to look. So, let's suppose we have this case where we have nodes 1, 2, 3, trees A, B, C, D, and this is too deep, right? So now this left part is too deep. Then we do a rotation and we rotate we do this rotation, which has a name maybe. Basically, we just do so when you do insertion, you can break the balance requirement by at most 1. So it has to be that this could have, if this had height h, then this whole thing is going to have height h plus 2. Yeah, so this could have height h. So then you've got h plus 1 plus 2 and h. So this is the rules. But now this is height h. So these say that these aren't breaking the rules. And now you say, oh, well, this has height h. Oh, look, it obeys the rules. Everything is good. So then the other case is it's right degenerate, and the other case is it looks so this is the rotation, and you just sort of have to, there's only one other case really, which is sort of like when you have 1, 2, 3, A, B, C, D. And to deal with this case, if this is too deep, then you do, you rotate this up and you get this case. And then you rotate it again and you get this case. So in the 1 minute that remains, I am not going to be able to show you, okay, if you have the maxima for each of these trees, Right, so you have some red value, like R1, R2, R3, and you have some green value, which is GA, GB, GC, GD. Okay, when you do this rotation, like this, and it's the same in the other cases, well, the G values, you haven't changed anything in these subtrees, right? So the maxima here, at the root, it stays the same. GA, GB, GC, GD. And now you have to say, well, okay, the R values are the same because they're associated to these keys. R1, R2, R3. So the only thing you have to work out is the green values at 1, 2, and 3. Yeah, okay. And how do you do that? Well, the green value here is max of R1, GA, and GB. Here it's max of GC, R3, and GD. And here it's the max of this green value. So max R1, GA, GB. Max R3, GC, GD. And this is going to be max of these two. Max of R2, this thing. Let's say that this is G1. This is G3, G1, G3. So when you do the rotation, you can update the maxima, the green values. Okay, so I'm out of time. So this isn't hard. When you do the rotation, maintaining your AVL tree is not such a problem. And this, okay. So this is not so hard. So in the book, they have a chapter on, or a section, chapter, I think, on augmenting data structures. This is called augmenting a data structure, except in the book, they talk about red-black trees, and here we're talking about AVL trees. But you can use red-black trees if you like. Okay, I'm 2 minutes over time, and I'm hungry. Okay, everybody, questions? Everybody happy? Okay, good. Thank you for letting me go 2 minutes over time. I will stop the recording. Yeah. Okay. No, it didn't record. Uh-oh. Okay, maybe we're going to be on Collaborate Ultra.